Hi, welcome to this video on calculating the pH of weak acids. So this is going to be a little different. There's a little more involved to a weak acid than when we calculate a strong acid or a strong base. So we're going to focus mostly on the equilibrium portion of it because that's really the big difference. When we're calculating the pH of a strong acid, we assume 100% dissociation or really high K value. So our equilibrium doesn't even include reactants. In the weak acid solution, there's only partial dissociation. So since things are only somewhat dissociating, we see that there is more of an equilibrium expression where we have products over reactants. So calculating the pH of a reaction when it's a weak acid, right, and we're trying to calculate that, is going to be using an equilibrium expression, which is a little, we've practiced, we've done, so it's more of an application of general equilibrium. So obviously, first thing we want to do is use a rice table. We learned that rice table method. It really helps. It makes things a lot easier. Make sure you don't mess up any numbers. So you write your balanced equation, then you set your acid-base equilibrium expression equal to your Ka value. And then you look at what is my initial concentration, how is it changing, what are the final concentrations. And then you substitute in and solve for X. Now that's where you have to pay really close attention because you have to think about what is X. So here's a little more detailed direction of what to do over here on this table on the right. I'm going to work you through a few different problems and have you do a few on your own. Okay, so let's start with this one. So in this example, it's saying that we want to calculate the pH. So we want to know where it falls on the pH scale of a 1 times 10 to the negative 4 molar solution of acetic acid. The Ka of the acetic acid is 1.8 times 10 to the negative 5. So this is really important because earlier in other units, we talked about the difference between a strong acid, strong base. And I specifically talked about how concentration doesn't make an acid or a base strong. So the Ka value is really tells us whether or not something is strong or weak, or how strong or weak it is. The smaller the Ka value, the weaker it is. So when really strength is the equilibrium. The pH is based on your concentration of hydrogen ions. So this is giving me the concentration of the entire solution of acetic acid. So a couple of important things when we're setting this up. First, we want to go back and think about our acids, right? So a lot of times you'll see me use a generic equation where I say HA put into water. Well, that's because, right, an acid, anything that is an acid, we use HA, right? And so that's going to donate a hydrogen. And so when it donates a hydrogen in equilibrium, you're going to end up with H3O plus and your A minus, meaning you end up with the hydrogen ions and then some sort of conjugate base. Well, what we're looking for is the concentration of hydrogen ions because that's going to allow us to find the pH. So that's just a generic equation, okay? And so that's really important. So keep in mind when we plug into our Ka expression, you would set up your Ka, we would ignore the water, right? So Ka would end up being concentration of H3O plus times concentration of A minus. And remember, when we say concentration, we mean molarity, not moles, over the concentration of acid. Now, if this was a strong acid, we wouldn't need to do this. We would assume 100% concentration, or not concentration, 100% dissociation. And so therefore, we wouldn't even need to set up a Ka expression. We would just assume all of my ions came from the acid. So here we go with what we would set it up. So same idea down here, but we're using acetic acid. So you can use either one. You can, when you're solving for this, you can use the HA generic, or you can write the actual formulas. So let's look at my equation I have going on here. So I have the acetic acid, which I know is HC2H3O2. And I'm going to add that to water. And when I add that to water, I'm going to see equilibrium happen, make H3O plus, and the acetate ion will then be a conjugate base and be able to accept hydrogen ions. Okay, so from here, this is really important. pH, to calculate pH, we need H3O plus at equilibrium, right? So we need to know when I put this acid into the water and it dissociates, how many hydrogen ions are floating around. So initially, the problem tells me I have 1.00 times 10 to the negative fourth molar solution. Make sure you're using molarity and not moles. And we're going to assume we don't have any of the ions. So as things change, now this makes acids and bases really nice, is we pretty much only change by one hydrogen every time. So it's always going to be minus X. We don't have to pay attention to, and then plus X for your products. We don't have to pay as much attention to our stoichiometry on this because, or the 2x, the coefficients, because of the fact that it's always going to be 1 to 1. And then at equilibrium, we are going to have 1.00 times 10 to the negative fourth minus X of my acetic acid, so there's less of that. And then we're going to have X and X of H3O plus and acetate ions, because that's how it changed. So then from there, you're going to plug in, you're going to set up your equilibrium expression. So our Ka value is going to equal our concentration of H3O plus. Remember, that's really what we want, times the acetate ion, which is my conjugate base, over concentration of HA. Now, one thing you want to pay really close attention to when you're setting this up is that you're making sure you're including those charges on there. I know I talk about that all the time in class and whatever, but it is really important. So once we go to set this up, it already gave me the Ka value. So I know the Ka value is 1.8 times 10 to the negative fifth. That's going to equal, I'm going to go ahead and plug that in. It's going to equal X times X, right, over, and 1.00 times 10 to the negative fourth minus X. Now here is a really important scenario. Remember on the AP exam, they're never going to ask you to do a quadratic formula. But if you were to try to solve this, you would end up with a quadratic formula. You can use a quadratic formula solver if you are taking this in college, but not necessary for the AP exam. Instead, what we do is we look at what's happening here. The amount of X, because this is a weak acid and this Ka value is 10 to the negative 5, is a really small dissociation. That means that when we take this minus X, that minus X is a really tiny amount that we're subtracting off. So in the long run, with that concentration already being small and we're subtracting a really small quantity, we don't really care about this minus X. So that's what we call neglecting the X. So if you do it with an equation solver, you're going to get a really, sometimes it's a little bit different of a number, but not enough to drastically change your pH or anything like that. So that change in the HA concentration is very tiny with weak acids. So from there, you're going to neglect the X. You're going to go ahead and do the math. So you're going to multiply 1.8 times 10 to the negative 5 times 1.0 times 10 to the negative 4. And then this is going to be X squared. So then you're going to square root everything. So when you solve, you're going to solve for X, and X is going to end up equaling 4.2, oops, I lost my pencil, 4.2 times 10 to the negative fifth, right? And that's going to be a molarity. And what we want to know is what is X, because this is really important. If we come back up here and pay attention to what our equilibrium says, X is the same thing as H3O plus. So that's my concentration of H3O plus. So once I know that, I can really easily calculate, go in here and calculate the pH, right? Because pH is negative log of your H3O plus concentration. So once I know how much H3O plus there is in the solution at equilibrium, super easy to go ahead and calculate that. So my pH is going to be negative log of 4.2 times 10 to the negative fifth. And when I plug that into my calculator, pull this up a little bit, I'm going to end up getting a pH that is equal to, so sig fig wise, when we do our sig figs for pH, the number of sig figs that I have, so there's 2, is the number of decimal places I want my pH to have. So 2 sig figs means I should have 2 decimal places. So it comes out to be 4.37 as my overall pH, which should make sense because it's acidic. It's a low, or it's kind of in that mid-range in the acidic range between 0 and 7. So that helps me recognize it's a low concentration of acetic acid, so its pH is kind of indicating that it is a weak acid. But remember, we can't use pH only as a way to know something is a weak acid. But because it's in that mid-range, that kind of tells me about where it's falling. All right, so that explains that question. Let's go on to the next page. Okay, so with exercise 11, I want you to try this one on your own. So we're going to go in and you're going to do this one on your own and submit that with your notes. So that should be one that you've done by yourself. When you're done, I will give you the answer. Your pH is going to be 4.23. Okay, so when you're finished, that's what you should get if you do it correctly. So please double check and make sure that you get that pH as you're working through it. If you don't, you can log in and ask me questions and bring those questions with you. All right, let's look at a different type of question. So in this question, it says determination of pH when there's a mixture of weak acids. So this is really important because in this scenario, it says only the acid with the largest Ka value is going to contribute appreciably to the hydrogen concentration. So that usually means that there's a big enough difference in the Ka values. You know that the amount of hydrogen ions that we get from the weaker acid is not going to be a whole lot. So it's not going to make the pH change drastically. So determine the pH based on this acid and ignore any others usually. That's what you would do. Now I'm going to prove that to you in this example, and we're just going to do 2 parts to this problem, but that's essentially what you would be doing. So I'm going to show you why that will work, and then I'll talk about we'll get the answer. So it says calculate the pH again. So we want pH, right, of a solution that contains 1 times 1.0 molar HCN, right? So there's acid 1, and 5 molar HNO2. Now the biggest thing here is to pay attention to the Ka values. So from what we know, right, the HNO2 is the less weak of the 2 acids, right? So since it's the least weak, it should contribute the most to the pH. And that means the other one's not going to contribute appreciably. So what we're going to do is we're going to first find the pH. Well, that means we're going to pay attention to, I'm going to show you both, but I'm going to show you that this one is going to be the one that really makes the difference. And that's the one we would normally care about. Okay, so normally you wouldn't have to do this twice. But the question also asks you to calculate the concentration of cyanide in the solution at equilibrium, so we have to do both. All right, so first thing, we know that this is, the HNO2 is going to be the least effect. The most effect. This is going to have no major effect. That's what we should expect to happen. So no major effect on the pH is what we're looking for here. Okay, so same as always, we're going to set up a rice table. In this case, we're going to do 2 rice tables because we're going to do 2 problems. So we're going to do part 1 with our first one. And so I'm going to write kind of small on this just so that I can fit both. But with this, we're going to have HNO2 plus water. And when that dissociates, we're going to end up with H3O plus and NO2 minus. All right. So when we look at initial quantities, right? So our initial amount here is going to be 5 molar. Again, remember we use molarity, not moles. And we're going to start with 0 of these. And so my change is minus X plus x plus x. So remember, your rice tables are really important because they do show that you know what you're doing and that you don't make a mistake. It also is important if we started with common ions and stuff. It would help us recognize we started with some initial hydrogen ions or something like that, which we're going to talk about in just a sec. So in this scenario, so this one would dissociate first, right? Because it is the highest Ka value. And so when we solve for it, we're going to have, I'm going to do this over here, my Ka, which is going to be 4.0 times 10 to the negative fourth is equal to, that's going to be equal to H3O plus and A minus, oh, not A minus, we're going to go with NO2 minus. Sorry, I tried to, sometimes I like to use the generic form a lot of times, so I tend to do that wrong. NO2 minus over HNO2. And then we plug in our values, right? So 4.0, 10 to the negative 4 is going to equal, and it's going to be x squared. Remember, we're going to end up over here neglecting that x, right? So when we plug that in, it's going to be 5.00 molar minus x, but we're going to neglect that x. So then when you solve for x is going to equal, and we come back here and look, remember that x is your hydrogen concentration, because that's what it is at equilibrium over here, okay? And we solve for that, and that's going to give us 4.5 times 10 to the negative 2 molar. Okay, so from there, we could calculate our pH. We know that's the one that's going to contribute appreciably. So that's the one thing I want to kind of point out. So when we set that up, okay, and you plug that in, pH equals negative log of the H3O plus concentration, we end up with, and there should be brackets, I'm sorry, I got a little lazy right there. My brackets look more like parentheses. Plug that in, and with 2 sig figs, we want 2 decimal places, it's going to be 1.35. Well, remember, in our acid-base strings, even though this is a weak acid, the 5 molar is really high concentration. So that means that we're going to have more hydrogen ions in solution because of that. So this is really what the answer should be, really close to, okay? Now, the second part of the question, though, then asked me to find the concentration of cyanide. So your acid that has the greater Ka value is going to dissociate first, or the most. So in your second part, I'm going to switch colors on this. I'll do it in blue. For part 2 of this, okay, we want to answer that second part of the question. We're going to look at the other equation. So in this scenario, we've got HCN and water, right? And so when I add that to water, hydrogen gives over, we end up with H3O plus and CN minus. All right, so from here, our initial for our HCN is the 1 molar. But this is a common ion problem because our HNO2 dissociated first. That means that we have up here some hydrogen ions already floating around. So this is one of the reasons why. So this initial is 4.5 times 10 to the negative 2 molar, but we don't have any CN. So this is a common ion type problem when we have a mixture. So if we wanted to find the amount of the ions, right, we know that if we start with some H3O plus, it's going to make it less soluble, which means we're going to make even less H3O plus with the HCN being there. So it's not going to change the pH much, but it is definitely going to change the concentration of the cyanide ions that we have. So that's really important to make sure that we realize this is a common ion when there's a mixture, because we have some of that left. So our change is still the same. We're going to do minus x, plus x, and plus x. So our equilibrium amount, right, is 1.00 minus x, 4.5 times 10 to the negative 2 plus x. Make sure my negatives make sense, my little decimal there. and X for my cyanide. So when we go to solve this, I'll move this over just a bit. Same scenario as before, we're going to plug into our Ka expression, right? So we're going to come back over here and we're going to say, all right, we know that this is 6.2 times 10 to the negative 10. That's going to equal, and I'm not going to write, I'm going to write it out, but H3O plus times Cn minus over HCN, okay? And so then again, as before we talked about, we're going to neglect the plus or minuses X. These are going to be so small that we don't really care about plus or minus X. So when we go to plug in, we're not going to include those. So it would be 6.2 times 10 to the negative 10 equals, and that's going to be 4.5 times 10 to the negative 2 times X, because we had neglected that plus X, over 1.00 molar, right? And neglecting the minus X. So when we solve, we're really solving directly for X. So this is important. In this scenario, X is the concentration of cyanide, which is what we wanted the answer to be. So we solve for X. That is the concentration. And so we get 1.38. And actually, I think that should be 2 sig figs. Ignore me. Hold on. Let me erase that off. So it comes out to be, 1.4 times 10 to the negative 8 molar concentration of cyanide. So there would be my answer. Now, think about that. If we took that quantity from the H3O plus, is it going to change 4.5 times 10 to the negative 2? No. So if I came back over here and calculated my concentration of H3O plus that we get here, again, adding that in is not going to make much of a difference to the concentration of H3O plus I got from HNO2. So that's where the whole scenario of my pH is not going to appreciably change, because if I take this and I add 1.4 times 10 to the negative 8 to it, right, I essentially still have 4.5 times 10 to the negative 2. So the pH of your greater Ka value or your less weak acid is going to be the one that makes the most difference on your overall pH. But we did need to do the second problem to be able to calculate out what the concentration of Cn minus was. Remember that whichever one you had that was a greater Ka value or less weak is going to be dissociating first. So we use that as a common ion. All right. Okay, so in this next problem, we're going to be looking at calculating a percent dissociation. So I'm going to show you one and then I'll have you do one, okay? So not too hard. Percent dissociation is really just thinking through what would percent be, right? So it's using a little bit of our common knowledge. So anytime we're talking about a percent dissociation, obviously if it's a strong acid, it's going to be 100% dissociation. That should make sense. But that's not the case with a weak acid. So we know we can compare strong and different variations of weak by their percent dissociations. And so that's why that's nice. So the percent dissociation, when we use that term, right, is really helping us out. So percent dissociation is a percentage, right? Dissociation means the breaking apart into ions. So it's the part out of the whole. So it's basically the molarity of your ions divided by the molarity of your whatever initial acid or base. So keep in mind, it's, in this case, we're going to talk about acids, but it would be the same for bases, right? So in this scenario, it would be concentration of H3O plus over concentration of HA. And then to make it into a nice percentage, we would multiply it by 100, right? So you can do this with the base too. Then it would just be the concentration of hydroxide ions over the concentration of base. Same idea. But it's just how much dissociates, and then you can use it to compare. The greater dissociation, the stronger it is, right? or the greater it's going to fall to the right on the pH scale. Or not pH scale, on the equilibrium. Calculating the percent dissociation of acetic acid in each of the following. So all you're doing is you're just looking for those components. Well, you're going to start with the amount of acid. You're going to use your Ka value, and you're going to find your amount of hydrogen ions, and then you're just going to plug in. So it's not any different than what we previously just did. So I'm going to do question number 1 for you. All right, so on question 1, I'm going to show you exactly what you're going to do. So basically what we want is, this is HA, right? And so we have HA, we need H3O plus to find percent dissociation, right? So that's essentially what we're looking for. So from there, we're going to set up our rice table. I'm just going to do it down here below. So we're going to set up our rice table. So our reaction is going to be we've already done this one before, acetic acid C2H3O2 plus water. I'm going to go quickly on this one because we've already done that part. H3O plus, and then the acetate ion is my conjugate base. And so initially I'm going to have I'm going to have 1.00 molar of my acetate ion, no hydrogen or acetate. My change is going to be minus X and then plus X for each of these because I'm increasing ions. And my overall at equilibrium, I would have less of the acid and X amount increased of my H3O plus. My Ka is H3O plus times C2H3O2 minus. Notice I write these on every single one because they're probably points. Okay, so I always have it because I don't want to miss the point if it was an opportunity. So I always write my rice table. I always write my Ka expression because those are going to be easy points. All right, so then from there, once we have that, you can use that for both problems. That makes your other problem a little easier. So for A, right, we plug in the values that we have for that rice table. And so my Ka is 1.8 times 10 to the negative 5. And that's going to equal X squared, or X times X, over 1.00 minus X, right? And then again, as always, we're going to neglect that minus X. We solve for X. That's going to equal the H3O plus. If we didn't know that, we would come back over here and look. What does X mean? It's the conjugate base and it's the acid. So X is, when we solve, we plug it in, and we end up with 4.2 times 10 to the negative 3 sig figs. Is that right? Yes. So 4.2 times 10 to the negative 3 molar. So then to find my percent dissociation, right, we're just basically finding the part out of the whole. So we're going to take 4.2 times 10 to the negative 3 molar, which is my part of hydrogen ions, divided by my initial amount, which is 1 molar of the acid, and then multiply it by 100 to make the numbers nicer, right? And so my percent dissociation is going to equal very, very small percent dissociation, 0.42%. All right. So it is a decimal percentage. Don't forget to multiply by 100 though. So the percent dissociation of the higher concentration is pretty high. So what would we expect the lower to be? We're going to find out. Okay, we do that. So there is a low percent dissociation there. All right, pretty easy. So what you're going to do is you're going to go back in and you're going to do the work. Show me the work. Okay, so you need to go back in and show the work for A. All right, and when you do that, you will give me the answer for that one. Okay. Then question 14 has you, again, calculating the percent dissociation, but it's going the other way. It's giving you the percent dissociation, and it wants you to calculate the value of Ka. So I'm not going to do this one for you because I want you to do it yourself. It's the same thing we just did, but we're working backwards instead. So I'll give you a little hint there. So you're going to start with the percent dissociation, and when you start with the percent dissociation, you're going to find from that percent dissociation the amount of H3O plus at equilibrium, right? At equilibrium. So then you're basically working backwards in your rice table. So that would be what you start with, and then you're going to set up your rice table but basically remember that your H3O plus is at the equilibrium. So that will help you figure out what X is, right? And so then you can plug in to find the other equilibrium value. So set up rice table for finding all equilibrium values. And then once you know all your equilibrium values, right, you're going to plug into your Ka expression, into equilibrium expression, and you're going to solve for Ka. So pretty easy, so you're working your way backwards. When you get your final answer, obviously lactic acid, you could look that up. I'm going to give it to you. The Ka value that you should get when you show me your work is 1.4 times 10 to the negative 4 molar, or not molar, no, whatever. So that's the answer you should get when you do it. So your work should come out to that. If you don't get that, then something's off, okay? And that's your job to find out why. So I want to see the work. If all you do is turn this in, I'm not going to give you credit. I'm just going to send it right back to you. All right, so last one is the same thing we were just doing, but we're going to talk about the same concept in terms of weak bases. So weak bases are thought of exactly the same as weak acids. The only thing that's different is you're doing a different reaction, right? Your dissociation equation is different. And when you do your dissociation equation, that's going to make your equilibrium expression different as well. So when I look at the equilibrium expression for a base, I'm going to make hydroxide as a product. So now my equilibrium expression is a Kb expression or a base expression instead of an acid expression. That's the only thing that's different, really. So weak acids and weak bases otherwise are going to be worked the same. So one thing, again, we want to talk about is the generic formula that we would use. So it's really easy a lot of times to use the generic formula, which is to consider a base, and if I put a base in water. Remember we talked about Bronsted-Lowry theory. When I put a base in water, instead of donating a hydrogen, it's going to accept a hydrogen. So it makes water act as a base. Act as an acid. So it pulls one of the hydrogens away from the water. So then I end up with a B and a hydrogen ion, right? So BH+. So basically my base has one more hydrogen ion and increases in charge. And my water loses a hydrogen ion, which leaves behind the hydroxide. Well, the hydroxide ion is what makes it a base. The more the base steals the hydrogen ions from the water, the more hydroxides I end up with in my solution. The basically higher the pH goes. So my Kb expression is what we're going to write here because we have hydroxide. So if you ever see a Kb, you know you should be making hydroxide. So it's going to be the base ion, so BH+, times hydroxide. Keep in mind, now we're really looking at our concentration of hydroxide more than anything over that initial base concentration. That's for a weak. Now, if it was a strong base, then it would completely dissociate and it would make 100% hydroxide, right? The same thing. So we wouldn't have that base on the bottom because it wouldn't be there anymore. It would completely dissociate and there would be lots of hydroxides. So that's going to happen with like any alkali metal hydroxide. So sodium hydroxide, potassium hydroxide. There is no potassium hydroxide anymore. It's all the conjugate acid and its hydroxides. Okay, so in this scenario, the other important thing, and it reminds you right here, just to kind of help you out, that if you want to find the pH of a weak base, right, you have to remember that X, when you solve, is going to be your hydroxide. And so when you take pH, or POH, is now going to be the negative log of hydroxide. So when I plug hydroxide into that same formula, I'm getting POH. So to find pH, we have to remember that those two things, pH and POH, are going to add up to 14. So when you're dealing with bases, there's an extra step to find the pH. Okay, so if you pay really close attention to what is your X value, then it'll help keep you from making mistakes on that. So exercise 15 says calculate the pH for a 15 molar solution. So it's a pretty high concentration of a weak base, right? Because ammonia is a weak base. And again, I'm paying attention. It's giving me a Kb. So it's telling me that NH3 is a base. So it's helping me out there too. Because if it gave me a Kb, it's telling me what it's going to do in water. So first off, for my rice table, right? For my reaction, I'm going to start with writing NH3. There's my base. Plus water is going to make, well, what do we know? We know that this, if NH3 is acting as a base, it's going to take a hydrogen. So we're going to end up with NH4 plus one more hydrogen, right? And leaving behind the hydroxide. We have to leave behind that hydroxide to ensure that it's a Kb expression. The initial concentration of the ammonia is 15 molar, and we're going to assume we're not starting with anything of the others because it didn't talk about it. My change, of course, is the same, minus X plus X plus X, right? And so at equilibrium, I'm going to have 15 minus X, X, and X. So my equilibrium expression is a little different, right? So when I do my equilibrium expression, I'm going to have a Kb is equal to the concentration of the ammonium ion times the hydroxide ion over the ammonia. If you're writing a Kb expression and you do not have hydroxide on top, something is wrong, okay? So that's really important. Ka should have hydrogens on top. Kb's should have hydroxides, okay? So we plug in and solve. So we've done this 8 million times now. 1.8 times 10 to the negative 5 equals, and we're going to have X times X. Remember, we're going to neglect the X just like we normally would. So I'm going to go ahead and write it in, but then I'm going to go ahead and say, well, we're going to neglect that and get rid of it just so that you have it on your paper. And remember, that's what I did. So here's where it was reminding you or telling you in that initial thing. When we look at X, if we go back in and look at X, X is the ammonium concentration and it's the hydroxide concentration. Essentially, we care about the hydroxide concentration. So X is the concentration of hydroxide. So when we solve for this, okay, we're going to get you can put it in either one. I'm going to put it in scientific notation. 1 point, and I want it 2 sig figs. So 1.6 times 10 to the negative 2 molar. Now here's the deal, is I want pH coming back up here. What I can do with this hydroxide is I can plug in, but if I plug a hydroxide in, I'm not getting pH, I'm getting POH, right? Because whatever I plug in is the P of that. So that's going to be negative log of 1.6 times 10 to the negative 2 molar. And so my POH is going to end up equaling 1, and remember 2 sig figs for my molarity gives me 2 decimal places. So that's going to give me 1.79. Okay, so from there, I want to calculate pH. I want to make sure I answer the question. So pH plus POH, right? So POH is basically going to equal 14 minus the 1.79. So my pH equals, keeping those decimal places, is going to be 12.22. No, 12.21, my bad. 12.21. All right, so the 14 is not considered significant. So even though it doesn't have any decimals, it's a whole number, so it's not considered significant. So you go with the 2 sig figs of your pOH. So 12.21. Obviously, that should make sense, because if this is a weak base, my pH should be over 7. If we put pH is negative 1.79, that would be a big clue that something was wrong, because that would be indicating that this was an acid. We're solving for a base. So use your answer and think about if your answer makes sense before you just stop working, okay? So essentially that gives us our answer of what we were looking for. So exercise 16 is another practice problem just like that. So again, I want you to do this one on your own, okay? And see if you can work through it. It's the same thing we just did. So it's methylamine. It doesn't give you a formula for methylamine. So what I would do is do my generic equation. I would just make this B, right, for a base. So when you're doing your reaction, if you don't know the equation or you're getting confused on the equation, just do a generic. The base, which is the methylamine, plus water is going to make, and then we know it's a base, so it's going to make BH plus and OH minus, right? It doesn't matter. It's going to work out the exact same way. So your methylamine is just this. Pretty easy. So anytime you're given a reaction, so like the lactic acid one, you can use a generic equation. You don't have to know the reaction. You can use a generic equation for any of them. As long as you're using either the acid generic equation or the base generic equation correctly, they're going to give you credit for that. So it doesn't have to be perfect. So keep that in mind. You can just use the generic if you get mixed up. Flip back over to that. All right, so I want you to do that exercise 16, and then that's the end of our weak acid base calculation video. I know that was kind of a lot, and I gave you some practice problems in between, but this is probably the hardest part of this unit. So that is one of the harder things in this part of the unit for acids and bases, but otherwise not too hard because it was just an application of our equilibrium. All right, if you have any questions, send me a message, let me know.